Hi, good afternoon. My name is Christian Kutz. Today I will be joined on the stage by my colleagues Amit Shrivastava and Dilip Lukos, and later on Michael Chevelle from Symantec will join me as well. So today we're going to be talking about building highly available, secure, and scalable services using Azure networking services. The goals for the session are for you to learn about how you build reliability using Azure services into your specific scenario, how you build security and reliability and scale into your scenario. You will also learn where and when to use the different load balancing abilities in Azure, and you hopefully will walk away with an overview of what is new so that you can get started using these features. So load balancing is a really broad term, and we use load balancing for several different reasons. One is it allows us to define well-known endpoints and names for our customers so that applications can be reached to them. Load balancing, broadly speaking, is used to assure, scale, and secure your application. And you can simplify your scenarios with fully managed Azure products to help you. So let's dive a little bit deeper. You can use Azure Load Balancer for your scenarios and create scalability and redundancy. You can also choose to use Application Gateway and WAF to the Web Application Firewall to add additional Layer 7 capabilities. And lastly, you can scale out across multiple regions using DNS load balancing with Traffic Manager. So we have solutions for load balancing, whether that's Layer 4, TCP and UDP, whether it's Layer 7, HTTP, HTTPS, and we have a global DNS load balancing service as well. So here's a quick overview of all that's new. Again, this is an eye chart, as you might have seen earlier in the week from others. No, there's no quiz at the end, but we wanted to show you that we're serious about this space and that we're making substantial investments in this area, and we will continue to do so. So let's take a deeper look at Azure Load Balancer. Azure Load Balancer is part of the Azure SDN stack and has three fundamental scenarios. It's also a multi-tenant platform, so nothing gets spun up for you specifically. This is infrastructure is already there waiting for your programming instructions. It provides high performance and low latency for your applications, and it can be used as a public load balancer, as an internal load balancer, as well as for outbound connections to the public internet. It provides flow-based load balancing, and this is really important to remember in the session. All these load balances are slightly different, and of course provides health probing for that. It also provides in-mod NAT rules, so common applications would be your remote desktop sessions or SSH. And as I mentioned, we have outbound connections using Source Network Address Translation or SNAT. So I'm really excited to announce the new generation of our Azure Load Balancing platform. As a product, it's called Load Balancer Standard and is now available in preview in 6 different regions. It expands to your entire VNet. The previous generation of the load balancer has a restriction that it can only address virtual machines that are a part of an availability set. And through that, it had a limit of 100 instances in your backend pool. Those restrictions are gone in load balancer standard. So you can now have up to 1,000 instances in a backend pool, which also includes the 1,000 instance virtual machine scale set. There's also a new feature released as part of this product that's called HA ports, which allows you to balance and scale virtual appliances, and can also be used for a range of other scenarios for, say, you have to balance 10,000 ports and you want to create 10,000 rules. And we also offer new advanced analytics, and I'll talk about that a little bit later. And the other feature that is new, or ability that's new as part of this product, is the interactions with availability zones. So in the context of availability zones, load balancer provides cross-zone load balancing and a zone redundant load balancer. So if you take virtual machines, you deploy them in different availability zones. What load balancer does under the covers is it creates a zone redundant path with a single IP address for you. So it's a regionally anycasted address that is basically served by programming that's been replicated to every single availability zone that's available in that region. This works public as well as internally to your VNet. And it also applies to inbound connections as well as outbound connections. So I mentioned earlier, we now expand to the entire VNet, and I'm not going to go read through the list of scenarios on here, but it's important just to remember that load balancer really doesn't have a restriction of an availability set anymore. And now you can mix and match VMs. You can have virtual machines that span different availability zones. You can have virtual machine scale sets that go up to 1,000 instances. You can combine multiple virtual machine scale sets in the same backend pool. So you can now bring to life some of the virtual appliance scenarios, for example, with a fixed license and a pay-as-you-go license together. So now you can use all these scenarios and blend the instances as you choose. The other thing that is new as part of load balancer standard is the load balancer standard always requires a network security group to be applied to an instance or a public IP for that matter. Whether this is whether you use a public IP as a instance level public IP for virtual machine, or you use a backend pool, you always have to use NSGs, so you need to whitelist your traffic. So virtual appliance resiliency is pretty difficult in Azure today. If you've tried to do that, you might have been struggling with this. There is a blueprint that uses Zookeeper nodes. So now you have to deploy additional resources into your VNet. You can only support active, passive. The way this works is the UDR gets moved back and forth depending on what the status is of your appliances. It's really complicated and pretty limited. So with network virtual appliances with HA ports, this basically becomes a new reference architecture for virtual appliance scenarios. So now you can have per flow load balancing on all ports of an internal load balancer. This allows you to create appliance scenarios with inactive configurations for scale and resilience. And just a quick animation to show how this actually works. So basically, the UDR from the DMZ points to the ILB on the front end, and the same thing happens on the back end, and you get a symmetric path through your virtual appliance in the back end pool of the internal load balancer. So you guarantee that both halves of the connection end up on the same appliance. So this creates a very simple, reliable, and intuitive way to do high availability with appliances. So just a quick shot of what this looks like on the portal. The configuration for this couldn't be any simpler. You basically check a checkbox that says you want HA ports, and the load balancer takes care of the rest. Now, you do need to check with your virtual appliance vendor to make sure they're onboarded for this feature, because they ultimately are the ones who are fully supporting this from their side. And there's a variety of appliance vendors who are onboarding onto this feature right now. Some have already done that. So if you have a favorite appliance, check with them, make sure they have tested with this feature and are ready to support it. Let's talk about analytics, something that has been a bit of a challenge on the existing load balancer product. So we have now traffic counters for bytes and packets. They're fully integrated into Azure Monitor. You can select and filter and group these metrics. We also show you a view of what your inbound connections might look like. So this is basically reporting of TCP SYNs that are seen on the VIP, so that you can understand how many inbound connection attempts are being made, or assuming that they are. We also now fully expose the health probe status of every instance in the backend pool. So you can basically say you want to see the DIP availability, and now you want to have a filter, is what this screenshot shows, that says, okay, this is the one I want to see, or maybe I want to roll them all up into one. We also have a new data plane health measurement that's actually part of this platform, which allows a continuous data plane measurement. I'll talk about that in a little bit more next slide. We also have visibility into outbound connections, so now you can see how many snack connections are being made from your virtual network, And you can also see how many have failed. Thankfully, on this screenshot, the number is 0, and that's a good number to shoot for. But this will give you an idea of when you're running hot. So if you have outbound connection problems, check this metric. It will probably give you a hint as to what might be wrong. So let's take a little bit deeper look at how data plane health actually really works. So what this is it's a continuous measurement that's provided as part of the platform. The moment you program your endpoint, we start sending measurements to it. This is in-band. It's a load balance decision just like every other traffic. However, the virtual switch on the compute host blocks the packet from getting to the virtual machine. And so what happens is the vSwitch replies to the probing service, and we can establish what the availability of the data path is to all your compute hosts. So this is a new measurement. It is some insight into internal telemetry that we use to establish the health of the platform, so now you can see that as well. So quickly, outbound connections, or SNAT, is probably one of the least understood topics, and I'm not going to go into the details in this presentation because you could probably fill an hour with it alone. But I can't emphasize enough that you should take a look at this telemetry, because translation from private to public addresses is done through a fixed number of ports. So it's all the ephemeral ports that are part of the IP communication. And many connections to the same destination, which could be PaaS services in Azure, it could be a DNS server somewhere, it could be lots of different things, can exhaust the SNAP ports. This will tell you if you do. So common mitigation for that is you either configure your application to reuse connections or you assign public IP addresses to the VMs. So how is this exposed? So we introduced a new API version for the load balancer and public IP resources that is called August 1st, 2017. And it's a very simple change in the resource that unlocks all this capability. All the front-end configuration rules, NAT rules, back-end pool probes all stay the same. All you insert is basically the normal ARM syntax for specifying SKUs. So if you say SKU name standard, you get the new SKU. If you don't omit it, if you don't specify and you omit it, then your basic SKU, which is existing product, or you can also specify it. Important thing to note here is you must always use matching SKUs for load balancer and public IP. They both have to be standard or they both have to be basic. So let's take another look at a reference architecture. You might have seen something similar to this earlier in the week if you went to the AZ session earlier, I think it was on Tuesday. So this is a two-tier architecture that is a zone redundant web app with a database backend. So there's a zone redundant load balancer front end, which balances across all the zonal virtual machine instances, which have been spread across 3 availability zones, and the backend layer could be just about any database technology you'd like to use. So this is probably a picture you should keep in mind when you try to think about how you use this to build reliable applications. Let's dig a little bit deeper. The resources in that picture that we just saw are created this way. So the scale set is very simply specified. You have a parameter that says I want these zones, 1, 2, 3. Scale set automatically spans across these zones. Public IP, you specify just that you want a standard SKU, it's automatically zone redundant. And the load balancer, same thing, you specify standard SKU and it's automatically resilient across all zones that might be available in a region. If you wanted to create a zonal VM, VMs can only live in one place, so they're only in one zone. And the rest is pretty much self-explanatory. So the takeaway here is, while you can look at all the quick start templates for this, this is really simple. This is not something that adds a lot of complexity for you. It's generally all the complexity is actually underneath the covers. So let's do a quick demo. And this is live, so hopefully this will all work. All right, so this is a real deployment in West Europe. There's a standard load balancer in here, a public IP that's standard public IP. There's some instance level public IPs for virtual machines. There are 3 virtual machines deployed in here. They all run Ubuntu and Nginx. There's no tuning in here. It's no accelerated networking. This is just out of the box, install the server, and go. So let's take a look at these zonal VMs so you can see where you can tell which zone a virtual machine is in. If you look in the overview page, you can see that there's now a new field down here. It says which availability zone that VM is in. Let's take a look at another one. You can see this virtual machine is in availability zone 2. And the public IP is a standard SKU. You can see it up here. For load balancer, I'm going to show you a different place where you can see it as well, which is down here under properties. You can see in here what all the details are of this resource. So let's see if this works. All right, so I'm actually running a load test in the background because I wanted to show some metrics, and for metrics to actually show something, you have to have traffic. So this is on one of the VMs in Amsterdam that is receiving a bunch of traffic from this load generator, so let me shut this one off. So what you can see on this screen, on this view, is this is a very simple command that just does a curl to the front end of the load balancer and basically retrieves a file that lives in the load balancer. It shows which VM you landed on and which availability zone it landed on. So there's a sleep in here. This isn't full rate so that you can actually see it rather than it just scrolling by. Just to show you what the performance actually looks like. So this is PLA, which is an Apache Bench clone that is written in Go, I believe, which basically generates load for 5 seconds, 250 concurrent connections, and retrieves a 1 kilobyte file from the servers. And one of the things you can see in here is, this part's interesting. So now you can see the fastest time is actually incredibly fast. 5/10,000ths of a second is what this request took to complete. But there are some that took a little bit longer. Remember how AZs work? AZs are separate data centers, right? It takes a little bit of time to get from one to the other, so this is what you see. But you can still see that the bulk of the responses were completed in a very, very short period of time, and everything was successful. So let's take a look at telemetry real quick. Let me start the load generator back up. So as I mentioned earlier, the telemetry is integrated into Azure Monitor. And so if you take a load balancer and you want to see how much traffic went through it, you can select this here and see average. So the measurement pipeline in this 24-hour view hasn't quite caught up with the fact that we turned it off, but we should see it here. So you can see the drop-off in the average from when I shut down the load generator for a couple minutes. So now if you want to see additional metrics, you can overlay them. You can layer different metrics on top. But what I wanted to show you is what packets and connection attempts look like, and that doesn't look very nice next to bytes. So let's do this here. So now you can see we have the average packet count over time, and you can see how many connection attempts were made. Don't worry about this fall off here. This is to do with the load balancer, and as soon as the telemetry pipeline catches up, we'll get data again. What you can also do is you can decide to add filters to this. So I'm just going to give you a quick view of what that looks like. But actually, the health probe status is what everybody wants, so let's take a look at that. All right, so this is the health probe status for my pool, is 100%. Let's say I want to see this by a specific address. So you can select out of the backend pool which address you would like to see, and the telemetry will instantly filter that. You can pin all the stuff to the dashboard, so you could have it back here if you would like to do that. This will be directly integrated into the load balancer Blade in the next couple of weeks. How do I get back? All right, so yes, so this is the scenario we just looked at. So here are the takeaways. You can use load balancer standard for TCP and UDP scenarios for larger scale, greater flexibility, support for HA ports, new metrics, and availability zones. In this table, there's a partial list of the differences, and I think I will just leave you with that. So to wrap up, if you want to learn more about load balancer preview, please go to that URL, aka.ms/lbpreview. It's available now in these 6 regions, and 2 of those support availability zones with more to come. And with that, I'd like to turn it over to Amit, who will take you through Application Gateway.
Thanks, Christian. So, as you know, load balancer has been there ever since Azure started. And there are many scenarios, specifically with the web applications or REST API-based applications, where you want to take advantage of layer 7 specific routing. Maybe you want to route based on a URL or host headers. Maybe you want to do some cookie-based affinity so that your entire session is sticked to it always goes to the same backend VM. Or maybe you just want to secure your application, provide more TLS security, or have a web application firewall. And for these scenarios, you require something more than a flow-based load balancer, and that's why we had launched Azure Application Gateway a couple of years back. So let's go a little bit deeper into Application Gateway. This is an overview slide. It's not possible to cover each and every feature detail, but I wanted to just show an overview of what we offer today. We offer a lot of layer 7 specific routing. We do true HTTP round robin. So even if you have on the same persistent connection, you are sending multiple HTTP requests, it would not end up on the same backend VM. It would actually do a round robin to your entire backend pool so that the load is evenly distributed across your backend VMs. We also do a session-based cookie affinity, which is managed by the gateway. I'll cover those in details. We do URL-based routing, where you can have independently scaled backend pools for different URLs. For example, you have a blog site which is receiving a lot more traffic. You could have an independently scaled backend pool for that. You can also, for better cost optimization, you can load up to 20 websites today. We will increase that number more, but you can have 20 different websites like fabricam.com or contoso.com as shown here behind the same application gateway. Or you could have up to 20 different subdomains. For example, if you are contoso.com, you could have blogs.contoso.com, api.contoso.com, all going to its own backend pool, and all you can scale independently. In security, we, of course, do SSL termination to free up your web farm. I'll go into a little detail about there. We also offer you SSL policy. We have made new announcements on SSL policy. Now you can control not only TLS protocol version, but also the Cypher suite. And we also provide end-to-end SSL. So us being a managed reverse proxy, most of the time the SSL is terminated on the gateway and it flows to the backend over plain HTTP. But if you want, you can re-encrypt your connection to the backend pool. And there are many scenarios, I'll cover that. We offer quite a lot of diagnostic features. Again, I'll cover those going forward. And of course, we do custom health probing. Now, main scenarios, like where do you think that you would use an application gateway? Well, we offer just both a public IP as well as an internal ILB IP. More importantly, you can have both of them present in a single application deployment. So your same application deployment can have a public IP exposed. You can CNAME that and have external traffic come to it. Or you can have an ILB IP only, and you can have your internal VNet traffic go, or have both at the same time. As I mentioned, we do a round robin on HTTP. So it's, even if it's a persistent HTTP connection or even a SSL connection, if multiple requests are sent, all of them are distributed evenly to the backend pool. What can you put in the backend pool? We are only restricted by the IP connectivity. There is no restriction whether it should be in the same VNet or it should be within Azure even. So if application gateway instances can reach, they can be part of your backend pool. So that explores, quite a lot of connectivity choices to you. You can use private IPs within the VM. You can use NICs, which are within that VNet. You can use VMs which are connected to another VNet, whether through public, the VNet peering, or they are publicly connected through IPsec tunnel using VPN gateways, or global peering shortly. So you can use private IPs in all of those scenarios. You can use cloud services which are part of the same VNet. Or you can have cloud services which are external to the VNet. In that case, you would need to use the public IP. You can even send traffic to outside Azure using public IPs. So there are quite a lot of scenarios. One scenario I wanted to highlight especially is you can connect to on-premises for two kinds of scenarios. Your backends could be going to the on-premises. For example, you have few databases which are on-premises. So the traffic is coming from public IP and it gets routed to the backend VM. That is possible if you have on-premises connectivity through VPN or express route. We also can do it the other way. You can have your on-premises VM connecting through an ILB IP to application gateway and then routed to VMs which are within Azure as backend pool members. So you can do it both ways. We offer full hybrid connectivity over there. SSL management, of course, we do SSL termination. This frees up your websites to to focus on their web application, the business logic, and not worry about costly encryption or decryption options, right, scenarios. So you have a central place where you manage your SSL certificates. We also offer SSL policy, which I will cover in one of the next slides as a new feature. And as I mentioned, we can also do SSL re-encryption. Most of the traffic is encrypted on the gateway, and then it's sent to the backend over HTTP. You can do on a per backend pool basis optionally re-encryption. So you could have two backend pools, and you can say that traffic coming to contoso.com, let's say, is sent over plain text to one backend pool, and you can say maybe a fabricam.com requires more security, and traffic to that particular site's backend pool needs re-encryption. So you can turn on re-encryption for that particular backend pool. So you can do quite a lot of mix and match like that. One thing also important over here is that application gateway will only talk to known backend VMs. So you have to whitelist the certificates on the backend pool VMs. So it's just that you take the public key and whitelist it with application gateway. If application gateway knows about that particular backend VM, it would communicate, it will re-encrypt the session and it would communicate to that backend VM. Going forward, we support URL routing and multi-site support. So you can have completely independent backend pools which are routed based on their URL path. So you can have /videos goes to one backend pool and /images goes to a completely different backend pool. And you can have a default backend pool if there is no URL path match. The request goes to that particular backend pool. Importantly, you can completely independently scale these backend pools. So if your videos requires a lot more traffic, you can have bigger, beefier machines over there, or you could have VMSS, the virtual machine scale set in images, which will scale up and down automatically. So you can have up to 20 of these backend pools for URL-based routing. Similarly, we support multi-site hosting. So application gateway has only one public WIP or one internal IP. So we rely on either, if you are sending HTTP traffic, we rely either on the host header to determine which particular domain to invoke and which particular backend pool to send the traffic to, or we rely on TLS SNI extension, server name indication extension, to determine that if there is a SSL connection coming, which of the 20 possible different certificates to use to decrypt and send the traffic to the backend. So we support those. In diagnostics, we provide you many different types of logs, chief being access logs. Access logs are log of each and every request and response, and they provide details on quite a lot of interesting fields, like who was the client which called, what was the port on which the client was connected to, what was the URL client was using, bytes in, bytes out, how much time it took within within the end-to-end response, from the time it received the request to the time the last byte of the response went out, how much time it took within that whole round trip. It gives the latency on that. Also the status code which it receives from the backend. So this is done for each and every request, and it is integrated with Azure Monitor. So this log can flow directly to your own storage or event hub, whatever you are using, and then you can apply your own retention policies to store them for as long as you want. This log is generated every 5 minutes. It's not a sample, it's a log of every request. We also have performance logs. So application gateway has multiple instances for scalability and high availability. Performance logs basically indicates how these instances themselves are performing. So it shows data like what is the throughput each instance is receiving, what is the total request count on each instance, what is the average latency these instances are seeing, and what are healthy and unhealthy host counts on each of these instances. So it contains quite a lot of information from there. We also have one of those information, the throughput which each instance is saying is exposed as a metric. So you can see it on the portal. You can see what is the total cumulative throughput application gateway is seeing at this point. More importantly, you can set alerts on these metrics. So you can say, if any time my cumulative throughput across all instances increases beyond, let's say, 800 megabits per second, send an alert. You can integrate that with web jobs and write your own automation. So you could write an automation which says that if my request goes beyond a certain level, add more instances or do something like that. We also have backend health logs. So this is a real-time API. When you call it, it goes through each instance and probes the backend, and it gives you results of those backend health. So if you notice, it's not just the VM, but it also is looking at the port. So you can have, it is looking at the health information of VM and port combination. So this is a real-time API which is available right now. Coming to new announcements. So as I showed in earlier slide, we have always supported TLS protocol version SSL policy. So I'm very happy to announce that we now support SSL cipher suites as well. So now you can control your TLS protocol version as well as SSL ciphers which are supported on the gateway. And you can also set the priority order of that cipher suite. So this determines what is the cipher TLS protocol combination which is used in a full handshake, right? So this is available in two different choices. We have come up with 3 pre-configured SSL policy. We sat with our own security board, our own crypto teams reviews, and came up with these 3 SSL policies that we strongly encourage customers to adopt to the 2017 policies. They are numbered by day, by year, month. So there are 2 2017 policies that should give you SSL rating of A in any kind of SSL rating like Qualys or SSL Labs, etc. So we encourage you to use those 2. The 2015 policy is strictly for backward compatibility purposes. All the existing gateways inherit that policy. So we have eliminated from 2015 a few weaker ciphers, key being some weaker Diffie-Hellman key exchange ciphers. Now, that is our recommendation, but if you absolutely require to have your own custom SSL policy, you need to do that as well. So maybe that your organization does not like one of the cipher policies, cipher suites we have in our own pre-configured policy. So in that case, you can choose to create a custom SSL policy. It's very straightforward. Instead of using a pre-configured policy, you just set it to custom. And now you have to specify just 2 things. What is the minimal protocol version which you want to select? So you can say, I want to have TLS 1.1 and above, or you can say TLS 1.2, in which case it will just support that. And then you provide a list of ciphers in order. So essentially takes only those ciphers and works and allows those configured. You can see a list of all available ciphers with Application Gateway. So you can see all the current SSL policies. If we add new policies, we will enhance that so that it that API and PowerShell and CLI continuously shows you that particular, what are the available ciphers choice options, what are the policy options you have. And on a gateway which you have configured, you can also see what the effective cipher policy is at that point of time. We also announced, this is another very popular ask. A lot of times you want to have HTTP to HTTP done directly at the gateway. In the past, customers have set up dedicated backend pools whose sole job was to receive a HTTP traffic and do a redirection from the backend so that it comes back as HTTPS. So now we support redirection at the gateway itself. Now, it seems that the main use case is HTTP to HTTPS redirection, but it is much more powerful than that. It can do any kind of redirection. It's essentially a listener to listener redirection. So what you're saying in this case is that receive my traffic on HTTP and send HTTP listener and send it to the listener, which is HTTPS. So in the same spirit, you could also say receive traffic on .com and send it to .org, for example, right? Or you could even do an external redirection. You can say receive traffic on ABC, for example, contoso.com, but send the traffic out to fabricam.com, right? So it supports both global and path-based redirection. So you can set the redirection on an entire listener, or you can set the redirection on a specific path. So you could have a scenario where you can say that, hey, I have a contoso.com site, I'm okay with HTTP on most of the site, but I have a specific area, let's say a shopping cart area. So if someone visits contoso.com/shopping cart, only then redirect it to HTTPS. So we can do that as well. When you do the redirection, you have optional configuration choices, whether you want to have a permanent redirection or a temporary redirection. And you also have choices to indicate whether you want to include the original query string and original path URI, or you just want to do a blank vanilla redirect, a vanity URL kind of redirect. So we support all kinds of redirection, chief being HTTP to HTTPS, but you can use it for many other scenarios, including redirection on a specific path. That's available today. Now, another one of very popular choices was that today Application Gateway supports VMs, NICs, public IP, private IP, FQDN, VMSS, but many customers have asked that I have a Azure web app, and how will I support that? The problem over here is that these web apps and then many other kind of scenarios, they are themselves multi-hosted, right? So they are multi-tenant themselves. So there is one VIP on which there are multiple websites hosted. Now when we receive traffic, when Application Gateway receives traffic, it has a host header. But by default, Application Gateway preserves the host header. So for example, if we receive the traffic as contoso.com, we send it to the backend pool member as with the host header, the HTTP header set to contoso.com, right? So the backend website is actually configured as contoso11 or contoso22, and it is expecting a host header which will say contoso11.azurewebsites.net or contoso22.azurewebsites.net. We didn't do the translation for these websites, and therefore when the traffic actually reached the backend, Azure websites had no way of knowing which particular tenant to redirect it to direct that traffic to. So now we support Azure websites directly. There are two knobs over here. Again, like the HTTP to HTTPS redirection, the primary use case is support Azure websites, but we have designed it generically so that you can support any kind of multi-tenant website. So you have two knobs over here. You can either say, discard whatever is the incoming host header, and when you are going to the backend pool, always choose this particular host header. So you can have a backend pool where it will always say, all my, let's say, ADFS farm traffic will have a particular host header set to all members in that backend pool. Or you can say, pick the host header from the backend pool's members FQDN. So now you can have one pool, two websites. For example, contoso11.azurewebsites.net and contoso22.azurewebsites.net. And if you set the second choice, that pick the host header from FQDN, then when a traffic comes to, let's say, contoso.com, it can be redirected to contoso11 and contoso22 at the same time. So if in the round robin choice, it's the turn of the traffic to send to contoso11 pool, it will rewrite the header to contoso11. And if it's the turn of contoso22, then it will rewrite the header to contoso22. So you can have multiple websites in the same backend pool, and it will rewrite the host headers appropriately. Or you can just send all traffic to all members of bracket pool using a single host header. That completely up to your configuration. So that is supported. It does this through, just plain HTTP to the backend or HTTPS to the backend. Both scenarios are supported. So end-to-end SSL is supported as well. We have made enhancements to the custom probes. So far, when you create an application gateway, of course, you get a default health probe which does probing. And it has all those probing criteria. But then you can create custom probes where you are in control of your URL, where to probe, your retry, how much time to your retry interval is, how much time it should take timeout, what is healthy and unhealthy threshold, and what URI to go to. So you can control all that using custom probes. We have added 2 new parameters to that. Earlier, we were just waiting for HTTP 200 OK response back, and all we cared was 200 OK. And now we also do look at, you can optionally specify your own range. So maybe for your scenario, 302 is fine as a health probe result. Or 201 and 202 accepted is also fine. So you can say, support 200 to 202. So if the backend is returning 200, 201, 202, count it as healthy. The second one is also very interesting. Till now, we were not looking at response body at all. Now you can have a dynamic web page, health probe result page, where we will look at specific strings. So if your health page result says healthy based on its own end-to-end application logic, maybe it's trying to do a database connectivity, and only if it succeeds database connectivity, it says healthy. So we can look at those specific strings and determine the backend health. If healthy is not present, or let's say there is an XML element is not present, then we will count that as unhealthy. Application Gateway has supported WAF since last, and we announced GA in March. When we went GA, we have from then we have added support for CRS 3.0. It is built on mod security OWASP core rule set, and now we have added support for CRS 3.0 as well, and added support for many rule configurability, which I will cover. So there are, when we integrate with core rule set 3, there are a bunch of protections which we provide: SQL injection, cross-site scripting, any kind of hijacking attempts protocol, LFI, RFI, all those kind of baseline protections are pre-built into the application gateway. So all your 20 websites behind a single application gateway by default are protected against these common vulnerabilities. Now you can also do user configurable rules. So any WAF has this inherent issue of having false positives. These are built as general rules, and maybe your application has specific problems which is triggering a false positive, but it's not really applicable for your application. So now we can turn off rules 2 different levels. We can turn off entire rule groups. You can say SQL injection is not relevant to me at all. I don't connect to a database. Or you can say within SQL injection there are 100 rules, and most of them are fine. Only a couple of them are giving you false positive. You can go to those specific rules and turn them off specifically. So we support user configurable rules. We have rich monitoring, same as application gateway. When you choose WAF, you get everything in application gateway, all those monitoring, plus you get all those features as well, and plus you get WAF logs. These logs again are integrated with Azure Monitor. So anytime any rule is triggered, anytime anything is triggered, we log it. It flows through Azure Monitor, and it goes to storage, OMS log analytics, and you can do all kinds of sophisticated queries using log analytics, or you can just inject it into Event Hub or your own storage and integrate it with any CM system of your choice. We also integrate that with Azure Security Center. So now you have nice visual representation of how many rules were triggered in past 10 days, which are the most common attack patterns. You can see a graphical distribution, and this also allows CM integration as well. That is it from my side. I'll invite Dilip to take you to how to take it to the next step and make it global.
Thank you, Amit. My name is Dilip. I'm a program manager in the Azure networking team. So thus far, you heard from Christian and Amit about how to do load balancing within a region. But now I'm going to be talking about how Azure enables you to have high availability across global regions, performance improvements by having regions closer to your users and directing them to the right place. Quick question, how many of you folks have applications that have user bases that span more than a region, kind of like a distributed user? Great. So you guys are all good candidates for improving your availability by using multiple regions. So Traffic Manager is Azure's global load balancer that operates at the DNS layer. What it does in a high-level view is that if you have your region, if you have your footprint in multiple Azure regions, or even external to Azure regions, we look at the health of those regions. We are constantly monitoring it to see that it's available, it's ready to take traffic, and if so, based on the routing method that you specify, and there are multiple routing methods, we'll go through them deeper, but based on the routing method you specify, when a user connects at the DNS layer to look up where they should go to, Traffic Manager will pick the right endpoint for them and return it back. After that, the client connects directly to the server, and the traffic goes back and forth between the client and the server. A few things to highlight on the Traffic Manager is that, first of all, we made this service so that it's very easy to onboard. You can use the portal, PowerShell, CLI, SDK, or directly the REST APIs to actually go and create what we call a Traffic Manager profile, which will provide you with like a front-end DNS name. And to the back end, you can add different endpoints using their DNS names. And then you can configure how often Traffic Manager should check for the health, and you can configure what kind of probes Traffic Manager should send to check their health. You can send HTTP probe, we'll send HTTP probes, or we will try to make a TCP connection attempt. And based on that, we will know if the endpoint is healthy or not. And we also allow you to increase or decrease the frequency in which we check your health, so that if it's a mission-critical application where you want to reduce the downtime as soon as possible, there are settings in Traffic Manager, which we will go also later on in a future slide, which shows you how you can have Traffic Manager check the health more often, so that if something fails, we will soon enough start redirecting users to the healthier ones. A key tenet when we designed, built, and when we are operating this service is that we understand that customers want DNS services to be highly available. If your site is not accessible, if your application is not accessible, doesn't matter what else is working, right? So we engineered this to be highly available. We run it across the globe, closer to the major population centers where your users are residing. We run it over multiple Anycast rings so that even if there's a failure in one, we'll always fall back into other, and a lot more other back-end investments. So let's see how we can use Traffic Manager in conjunction with the other load balancer methods to increase availability and performance and scalability for your applications. So I mentioned earlier we support multiple routing methods. First one I want to talk about is what we call priority routing method. This is the scenario where, let's say you have 3 endpoints. You can set their priorities starting from 1, 2, 3, 1 being the highest priority. You can, and when you set it up this way, Traffic Manager will send all the incoming requests to the endpoint with the highest priority till it fails, at which point it'll fail over to the next one. So this is pretty much the basic failover scenario where you're fine with all traffic going there into one place, but if something were to happen, it needs to go to the next one. And the key point to remember here is that none of this, once you set it up, the failover doesn't require any manual intervention. The service will detect that something's not correct with the endpoint, it's not responding back, So it's not going to send any more users in there. It happens right away. And the next one is what we call weighted round robin. What this one does is that if you have a set of endpoints, you can specify the ratio of traffic that should go to each of them. One of the ways in which our customers use this type of routing method is when they have, when let's say they are coming up with a new version of the application, you want to let in only a small percentage of your users to go there. In this specific example, you bought up the new version in, let's say, central US, and you want 1% of your traffic to go there so that you can study how they're interacting. If needed, you can pull it back, make it better, put it back. Weighted round robin allows you to do that. The next one is a geographic routing method. This is something we launched a few months ago. This is essentially the routing method where you can specify region groups at a world, continent, country, and for a selected few countries at the state province level. You can create a set of regions, put them in a group, and say that if any request originates from this region, always send them to a specific endpoint. So it doesn't have to be the closest endpoint. You can say something like, all traffic from Spain and Portugal should always go to US West, not the closest one. Although that's kind of more of an extreme case. The way customers use this particular routing method is, when they want to comply with local data sovereignty methods so that they know the users are pinned into a data center. Or if they have like specific versions of their, let's say, web application that is customized for a particular geographic region like a country, you can use this routing method. One key thing I want to point out and trying to express in this graphic is that the region doesn't have to be the same region where the Azure is. So in this example, we have a setting where all users from India should go to the data center in Australia. You can totally do that. Any of these combinations are possible. The next one is performance-based routing method. This possibly is the one of the fastest growing routing methods within Traffic Manager. This is the one where you can specify that, okay, here are my 3 different regions where my app is running. When a user comes to see where they need to be going, please direct them to the best one. Best is defined here as 2 things. First of all, it's up and healthy running. Second is that it's the one that will offer the lowest latency for that specific user. So as an example, if you have, let's say, 2 endpoints, one in US Central and one in US East, and if an end user, your customer is visiting from, let's say, Ohio in the Comcast network, for example, we have network latency intelligence that will detect they are coming in from that particular region based on the source IP address of the resolver that's sending us a request. Then we know which one is better for them based on the data that we are constantly collecting. So in this case, they might end up going to US Central. But this is the data that we always are monitoring, so we are always updating our network latency tables. Like I said before, this is something that our customers have been using increasingly a lot because this provides their end users with like the lowest latency experience. Very important for latency sensitive applications like gaming or for example for video streaming. So we heard from customers and we invested more into making this better. This is a particular feature that we announced a few days ago, Traffic Manager Real User Measurements. What this does is that, remember I mentioned Microsoft is collecting network latency information from different user networks. This allows you as a customer to augment that information with the observations made from your customer base so that this routing is relevant and increase in accuracy for you. And also, this also ensures that if there are specific end user networks where your users or devices are placed, maybe some of these new upcoming IoT networks, you can use this feature to provide network latency information to Azure so that the devices and users from those regions will be routed more accurately. How this works is that there are 2 ways. So let's say if your client application is a web application like a website, you can go to Azure portal. You can enable this feature. You'll be provided with a JavaScript that you can then copy and paste into your web property. Now, after that, whenever a user comes in and a page is rendered, what the JavaScript will do is that it'll go and fetch a set of endpoints that it needs to measure. It'll download a single pixel image, look at the first byte latency, collect them together, and send it back into Azure Traffic Manager. This happens every time a user is visited, so that information starts coming in from your user base. The other way is that you can use the Visual Studio's Mobile Center, where we have published an SDK that can be integrated into your mobile application that will do the same thing. It will start measuring different Azure regions, and it will send the measurement to Traffic Manager. So we covered a bunch of these. Routing methods. Now, this is one of the very interesting and powerful ways in which you can use Traffic Manager. This is called nested profiles. This is essentially mixing and matching these routing methods at different hierarchy levels. So in this specific example we have on the board, we have a Traffic Manager profile that says, send the users to the best location. Oh, and if they are going to West Europe, send them further, divide that traffic into 5% going into some specific a different region, and 95% going into something else. So you can have this different levels of hierarchical profile setup to suit your needs. And we will also go through one example in the demo that takes advantage of this. One more announcement that we made a few days ago. We launched a new feature called Traffic View. What Traffic View does is it gives you an overall view of how where your users are, how they're behaving, sorry, not how they're behaving, what their experience is like, and what you can do to improve. Specifically, when you use Traffic View, you will understand where your users are coming from, what regions in the world, how many users are coming from these regions, like the volume, what is the average latency experienced by them to different Azure regions. So that's kind of like their experience index. And then the traffic flow patterns. Like for example, from California, San Francisco area, most of your users are getting directed into, let's say, these two Azure regions. This gives you actionable insight. For example, you can look at this and say, well, I have a lot of users coming in from Australia, but they are having bad latency experience. So one of the actions you could do is that you could expand your footprint into our data center in Sydney region, for example. That should improve it. These two features are something that we will be iterating on, and so look forward to launching more improvements in there. Okay, so it's demo time. But before I jump into the live demo, just want to give a quick overview of what we are doing here. So what we are doing is that we have a website called azignitedemo.com, which actually you can use your mobile to navigate to. It's hosted on Azure DNS, and that points to a Traffic Manager profile, and this is a nested profile. So what this means is that, let's say this particular application has the following need. It needs to be fast, so send them to the closest region. And in each region, we have set up application gateway with web application firewall, and there are VMs behind it. So we'll be demoing how application gateway protects you, and also how Traffic Manager can provide faster connections. So in this case, everything is good in the sense that you want all the traffic to go to the best location, except for some reason, you want all traffic from Singapore to go to USA, not the closest region. Doesn't matter if there's a better region, go to USA. So what I have done is that the first level is a geographic profile, where you say, rest of the world, go to this site. Singapore, go to US Central. Now the second level profile is that, go to the best one. So this is what it is. And I also have the monitoring settings in here, where for the parent profile, there you can see that we are monitoring using the HTTPS protocol. What Traffic Manager will do is that it'll send an HTTPS request and wait for like a 200 OK. Anything else, it'll consider it to be unhealthy. And we have also turned on the fast failover settings. Essentially, the first thing is that we put the DNS TTL to be 0, so that when I'm doing the demo and I'm turning on and turning off things, we won't be impacted by the cached previous responses. We also turned on fast probing, which means every 10 seconds we'll be probing. We'll be considering even the first failure to be a sign of unhealthy endpoint. You can set it up to be that check it like 3 times before marking it unhealthy. Then we also have the probe time interval to be 5 seconds. So having said that, jump into the demo machine. Sorry, Surface just slept for a second. Okay, so I had already set up the traffic manager profiles and the application gateway under each of these regions. Now, I want to simulate users coming from different parts of the world. So what I had done is that I had already gone ahead and created a few VMs in different Azure regions. So these are client VMs. They are just going to pretend like users connecting from those regions. And we have it up and running. All right, so let's first go to the East US VM. So if you look at if you remember the profile, for USA or for anything except Singapore, you should go to the closest region. And I'm running this app in 3 regions. I'm running it in Central USA, I'm running it in Northern Europe, and I'm running it in Japan East regions. So this is the VM in USA, so ideally it should go to Central USA. Great, so I can just type in a small command. It's a very simple app. So it just shows up here. Now let's go real quick, go to Amsterdam and do the same thing. www.azignitedemo.com. Feel free to add comments if you navigate to the website. In there, so you can see it went to North Europe. So that's the closest one to Amsterdam. Now here's a VM from Hong Kong, and I'm going in there and let me refresh this. So it's going into Japan East, as expected. Now let's take Singapore. So Singapore is the one where we said, don't go to the closest one. Always go to Central USA. Let's see. And it did. It went to Central USA. So that's multi-level traffic manager profiles and geographic routing and performance-based routing in action. Now this is the DNS layer. This is global region. Let's look at a single region and see how how app gateway can actually protect you using the web application firewalls. So here, what I have is, I have like a little bit of a script in here, which I'm going to the VM running in Eastern USA, and I'm trying to just inject it there, pretending to be like a malicious attacker. So you can see that the thing that used to work before, now it's giving a 403 forbidden access. Now I go there and I just put like something regular, my name or something, and it works. So somebody got bacon in there, which is great. So you guys should all be coming into the Central USA one, because we are based in Orlando unless you are VPN'd into your home office, which is somewhere else. Okay, so that's one example. Let's also try something else that's not really legit comment in there. So I'm trying to see if there's any vulnerability that would extract the file contents of the password file from there. And even if your VM is not secured against it, App Gateway knows that this is not right. It will go and kick you out of there, or kick the malicious user out of there. So that's another example. But hey, it's working. And I do like scary movies. All right, so another example of this this demo is where, again, for the same VM, let me go to bash. So first thing I'm going to do is I'm going to get the IP address of where this VM is. Sorry, 1 second. All right, so this is the IP address. And what I'm going to try to do is that I'm trying to do two things. First, I'm going to try to connect it using a secure or like a strong cipher, the ECDSA, the elliptical curve DSA. That's actually a good one. So let's go and try it. It made the connection over here. So let me zoom in so you guys can see it's connected. It's good. Now let's try to do the same thing with a weaker cipher. So by the way, this is app gateway that's accepting the TLS connection that's being made even before all the HTTP sessions, etc. Now we are trying to do the same thing with a weaker cipher, the Diffie-Hellman one, that as part of the standard SSL setup, it should not be. Okay, let me take this. So. I think it's connecting to the wrong one. So as you can see, App Gateway did not accept this because this cipher is not supported in App Gateway. So even at the TLS layer, you cannot even open an SSL connection with weak ciphers. Great, so while we were doing this App Gateway side of things, my colleague Amit here, what he did was that he went and turned off the whole Japan region. So Hong Kong was previously connecting to Japan. Now let's see what's going to happen when we go to Hong Kong, let's reconnect to the VM. So Japan went down, so Hong Kong should ideally be going to the next best one. I'm going to open a private browser just so that any browser level caching will not affect us. See, so this is the Hong Kong VM. It previously was going to Japan Azure region. Now that the Japan Azure region is down, it is actually connecting to the central USA region. This is where Traffic Manager, with no manual intervention, figured it out and move the users over to the next best available region. So this is my demo, and I'm now going to switch back to the slide deck. Bye. Okay. All right, so let me now switch back to the slide deck, and we heard from myself, Amit and Christian, but I really want to hear the voice of a customer. I'd like to invite Mike from Symantec to come to the stage.
Awesome. Is this working now? Excellent. So I want to take you guys through a journey. We started on our Azure migration about a year and a half ago, and we needed to get a lot of services over to Azure, and that includes billions upon billions of requests a day. Back-end telemetry, front-end telemetry, actual request services. So we're going to talk about how we actually got there, what services we took advantage of, and the cool part is these guys showed off a lot of stuff that we got to take advantage of right out of the package that just worked. We didn't have to go install VMs. We didn't have to do any magic. You point a couple things in the portal, and suddenly things are working. So I'm an architect in the Norton Cloud Services group. So that means that I drive the applications for everything in this list. So we've got reputation services. Everything from file, website, mobile APKs, and more. We actually do anti-spam as well. And those reputation services drive hundreds of millions of endpoints. How many of you guys have Norton or SEP installed on your phone or your devices today? Anybody? You're connecting to these servers right now, and you have been all day. We also have about 1.2 million backend requests per second. So most of what I'm going to talk about is front end, but it's worth just showing that, yeah, these things scale, and they scale well, and Azure's handling it in real time. In the messaging group, we have things like RabbitMQ. We have bridging for telemetry. We have backend analytics teams that are getting real-time streams from these front-end services. And of course, we have our management applications. Those are things that drive the endpoints, allow us to find them. We actually get policy and events from them. But there's two really important services that I want to talk about today. It's actually one in reputation and one in messaging. Okay, so we're going to break down those two applications. We're going to talk about how big they actually are and what Azure was actually able to do, which was impossible in our own data centers. Now, first up, Traffic Manager. I heard through good confidence that we are a top 3 user of Traffic Manager. Every single service we have in our stack is actually using Traffic Manager. We use it for a number of things. They talked about most of them. HA capabilities. When RabbitMQ goes down in East, it does. Sometimes we do it on purpose. We want to because we want to test if it goes down, what happens. Sometimes we can take it down because we need to do a full cluster update. Traffic Manager magically just makes it appear in another zone. So we go from east to west within 5 seconds. You can actually see our traffic levels trail off very rapidly and then show up in another data center. That allows us to do updates and planned downtime as well. So when we need to patch Linux boxes, we're not quite serverless yet, we're not containers. So we actually do planned downtimes, and ALB allows our SRE teams to actually go in there and click a little slider and move the traffic back and forth. Capabilities that used to require a ticket and multi-level people interaction are gone. It's down to a slider. So one step better, full automation next. Now scale. So I said we have over 150 million endpoints hitting these services. Okay, so Traffic Manager is routing people from the entire globe. Okay, it's not just the US. We are US heavy. However, it's all over the place. But what we did find is we have some back-end telemetry which was provided by us by the Azure group that we are actually doing over 1 billion queries a month. A lot of that is cached by endpoints, obviously. We don't constantly hit the back end, but we're actually hitting 1 billion times per month. And reliability and performance, we have not yet, in the 1.5 years that we've been on this, had any downtime in the traffic managers themselves. So that's a pretty impressive uptime for a 1.5 years. And of course, the worldwide DNS presence is stunning. One of the drawbacks to having our own DNS infrastructure was that it was within the data centers that the services are hosted. So when a DNS server or an appliance that was doing the wide IP balancing for us would go down, we would actually see a ripple effect, and it would take a little while to recover. That's no longer an issue throughout our stack. So that's where we sit with Traffic Manager, widely used. But let's talk about one of the applications that runs behind Traffic Manager. Okay, so Spock. A little bit of a journey here. Go back 6 years, I was asked to write a service. This was the first time I'd ever written a web service. I was the sole engineer, and I built something called Spock, Single Point of Contact. Do you guys know what GCM is or APN? You get push messages on your phone? Spock is exactly that, except for endpoints. So we can do Windows, we can do Mac, Linux, we do the whole suite, we do appliances. So all of our endpoints come up to Spock. 6 years ago, I started to build this. It's a lib event-based HTTP long polling server. So we built this. We threw it on a box that was directly connected to an edge router in a data center down in Ashburn, and we spun up 185 VMs over in AWS because we needed to generate enough clients to actually take Spock down. I think we set some records. We never publicized this. It's kind of old news now since it's 6 years old, but we were capable of getting 7 million concurrent connections on a CentOS box with no kernel modifications. And that was how we ran for a long time. So when we built Spock, we stood up 20 physical giant Dell 720s in Tucson and Charlotte, and we put a GTM in front of them. And what would happen was we just would do round-robin DNS. We had to expose Spock directly through an ACL off the router because there were no stateful appliances that you can throw in front 5 years ago that could handle 100 million concurrent connections. So we had to bypass everything, and we were sitting there, and it worked well. Latency was good. It's just ugly when you're working with it. You don't have any load balancer in front of you. You take nodes out and in, but they mean something because they're a pet server. They have an actual routable IP on every single physical box we had there. Okay, so that's kind of where we were. And moving forward, we take a look at this, and we're like, okay, time to move to Azure. So we started looking. We made some contacts over. We said, hey, ALB looks like it can do this. Maybe we can actually finally fix Spock, get it off the public internet, get out of spinning up 50 IPs because the 500K limit in Azure would have meant more boxes but smaller connection counts, which is totally fine. It's actually a better way to run. It's more HA in my mind. So we actually ended up putting Spock behind an ALB. Spock today there's 50 servers per region. We have East and West, and I'm going to show a little diagram in a second. We'll get to that in the next slide. But the impressive part is Spock sits at around 39,000 requests per second. The ALBs don't even hiccup. The response time of Spock is sub 2 milliseconds throughout those regions, and it's doing it at nearly 40K a second. We usually balance 50-50, thankfully, thanks to Traffic Manager, which keeps it nice and balanced. It's usually 51-49, just given, because it is long polling. Connections do tend to come up and ask for a 30-minute long poll, and then they get a reply or an event down. Inside, the average time to service the request between Spock and the load balancer is actually less than 2 milliseconds, proving that the internal Azure network is just as responsive as the ALBs, which is very important to us. We used to have switches that would cause issues. Older switches would actually cause internal latencies. That's gone. So in Azure, like I said, I already covered the Traffic Manager. We don't need to do round-robin DNS. The ALBs already supported 4 to 30-minute timeouts, so we can come up to the Spock server and say, hey, call me back in 25 minutes because I found my optimum network connection because I'm on a mobile somewhere out in a foreign country. It's 25 minutes. And Spock would sit there on that connection and then shove a response down and say, nothing has changed in the past 25 minutes, please reconnect. Then they come back. Hypothetically, if a policy update or something on our back end, there's a list of about 150 different events that can trigger this, we would actually shove a response down immediately, wake that client up for heavyweight communication to one of our back-end servers. So think of Spock as a hinting service that wakes people up and says, hey, you have something to do. Come out of your sleep state and function. Now, let's take a look. So here is the actual ALB scale and performance. So if you take a look at, I don't know how to zoom this, but you can take a look. This was taken the other morning. We have a 34,000 requests per second. We have about 12.3 million concurrent connections with 45 Spock servers healthy in both zones. And that's functional. Every day it does this, time in and time out. It's the first graph that I check in the morning. I get on my train, and I take a look, what's Spock doing? Then I check RRS and many of our other services. But the most interesting thing we found, Spock was connected at the perimeter of an actual physical data center that we had. We're trying to shut these data centers down. It's part of the Azure journey to get out of our own data centers. They're expensive, hard to maintain. But what we found was we did this switch over, and I remember I was actually in Culver City with our Azure representatives. And we did the switch over the night before, and we were sitting there like, oh, this is cool, this is working really good. And things were good, and we started pulling pingdom graphs up because pingdom does our worldwide monitoring of Spock. And we noticed there was a 60 millisecond response time drop in latency by simply moving into Azure, into these better systems. And we probably could have fixed that by updating hardware, but if somebody else is going to do it for you in the cloud, that seems like a much better way to do it. So that was Spock. Fast forward to another service. Now, the reason Spock uses ALB is we don't want somebody else to terminate our SSL for us. So there's reasons to add there. Also, Application Gateway has a different scale profile. So as we take a look at Shasta, this is probably one of our most important services. It's file reputation. It's how Symantec actually protects endpoints. This is for all of SEP. So this is enterprise customers too. It is actually very large traffic. So we see about 25,000 requests per second. When Microsoft ships a Windows update, we see 90 to 130,000 requests per second because we're scanning all those files that are now being discovered on people's machines and updated. It's pretty big. In the time that we've been having this presentation, which is a little over an hour, there's already been 1 billion backend events through the RRS application. Those are actually pumping, and somebody might be able to explain this. It's kind of a different presentation, but on the back end, RabbitMQ, we're doing ALB on the internal. You guys made reference to having internal ALBs. So there was about 1 billion ALB requests that flowed through our telemetry flow in the time of this presentation, with about 25,000 per second here. So we decided to leverage Application Gateway so that we wouldn't have to build up virtual appliances to actually do the SSL termination in this application. Okay, and we do have a very specific requirement of a maximum worldwide response time of less than 5 seconds. and we had to maintain that. So it was critical to us to test and make sure that application gateways could perform at least as good as a virtual appliance, which they should be capable of, and clearly they are. So we ended up landing on application gateways. The design includes the same traffic manager control for being able to balance traffic east-west, and very soon, the cool part is Amsterdam has already stood up. We are actually bringing it online now, and we're going for a third region that's going to use the fancy new performance-based traffic routing that was just spoken about. And that's going to allow us to reduce latencies even further in Europe to start with, and then we'll do Japan, and then we'll do many other regions. In order to terminate that traffic, however, though, we did have to come up with our own auto-scaling mechanisms. That's not quite ready yet. However, we do scale these up and down. We have 6 application gateways per region, with a significant amount of instances behind them to perform the SSL termination for these. And then, oh, it's you guys. Cool. Thank you, guys.